In the previous session, we have seen that the length of a smooth curve r of t is equal to x of ti plus y of tj plus z of tk, that is traced exactly once as t increases from t is equal to a to t is equal to b is L is equal to integral a to b square root of dx by dt square plus dy by dt square plus dz by dt square dt. The above formula can be written in the arc length formula in the short form as L is equal to integral a to b absolute value of v dt, where v is the velocity. If we choose a base point p of t naught on a smooth curve C parameterized by t, each value of t determines a point p of t is equal to x of t, y of t, z of t on C. Then we replace the variable inside the integrand in the above length formula to the dummy variable tau, the lower limit a by the constant t naught, and the upper limit of integration b to the parameter t. Then the above formula becomes L is equal to integral t naught to t absolute value of v of tau d tau. It can be seen that the right hand side simplifies to a function of t, and hence it is appropriate to denote the length by s of t is equal to integral t naught to t absolute value of v of tau d tau. It is the directed distance measured along C from the base point p of t naught to the point on the curve corresponding to the parameter t. If t greater than t naught, s of t is the distance from p of t naught to p of t. If t less than t naught, s of t is the negative of the distance. Each value of s determines a point on C, and this parameterizes C with respect to s. We call S an arc length parameter for the curve. The parameter's value increases in the direction of increasing t. That is, arc length parameter with the base point p of t naught is given by s of t is equal to integral t naught to t square root of x prime of tau square plus y prime of tau square plus z prime of tau square d tau, which is equal to integral t naught to t absolute value of v of tau d tau. Okay, this will be our base point p of t naught. We move along this curve. Okay, and suppose we are at this point at t, and we are asked to find the arc length parameter. Arc length parameter means the distance along the curve from the base point to reach this point t. Remember, this s of t is not the shortest distance like this. Okay, this will be the shortest distance. Shortest distance will be like this. Okay, instead of that shortest distance, we are considering the distance along the curve. Similarly, if we take another point here, say I call it for convenience, if it is a t prime, and its arc length from the base point, arc length between these 2 points, initial point and t prime, will be calculated using this formula. S of t is equal to integral t naught to the v of t, absolute value of v of t tau d tau, with replacing t with t prime. Okay, so the idea is that this new formula will help us to give a new parameter called arc length parameter. Arc length parameter we call as an arc length parameter, and we use the lowercase letter s. Also, we have to stress the point that the parameter's value, the parameter, what is the new parameter? S. The S increases in the direction of increasing t. Increasing t. Okay. So, depending on the value of t, we get a new parameter called S of t. We consider an example. If t naught is equal to 0, the arc length parameter along the helix will be like this, the same helix that we have considered in the previous example. So t naught to t. So after evaluation, you get the value root 2t. That means s of t is equal to root 2 times t, isn't it? So in the previous example, we have a movement from 0 to 2 pi. Okay, then how to find that arc length? We have to put t is equal to 2 pi. So we get root 2 times 2 pi, which is equal to 2 pi root 2. At the same time, if we put t is equal to negative 2, what happens? We get negative 2 pi root 2. Negative 2 pi root 2. That means we are moving on the opposite direction. That is the reason this arc length parameter is always gives a directed distance. Directed distance. Okay.